This series of videos will cover Chapter 3 of Greenberg's text on Advanced Mathematics for Engineers. Um, and that chapter is on linear ODEs of second order and higher. Now, the next couple of videos I'll give you an overview of ODEs in context, especially in terms of what we covered so far. We'll talk about how to recognize or define linear dependence versus linear independence of a set of functions of a variable. And then we'll talk about the general solution to the homogeneous ODE. You should have in mind that you'll be able to identify, the main goals that you'll have is that you will be able to identify whether a set of functions of a variable x, for example, whether that set is linearly dependent or linearly independent. And you'll be able to test or determine whether a given function represents the complete general solution to an n-order homogeneous linear ODE. Now, I encourage you to read through section 3, through these pertinent sections. 3.1 gives a nice sort of big picture outlook on these ordinary differential equations. So recall, so far, we've considered ODEs of first order. And we considered the linear case, which had the general form of y prime plus some function p of x times y is equal to some function of only x and independent of y, and we put that on the right-hand side. So we learned how to solve that. And we also considered some special cases of nonlinear ODEs. In particular, we looked at a function that was separable. That is, if y prime is equal to some function capital Y only of y times some function of capital X only of x, this could be solved as a separable equation. And we also looked at the case of y prime being equal to a quotient of two functions, a quotient of two functions of x and y, m of x and y over n of x and y, for example. And this could be solved as an exact equation and perhaps needing an integrating factor. That integrating factor was either a function of x or a function of y. So with these sorts of problems, we are able to produce analytical solutions. We looked at methods of producing analytical solutions. But we also considered situations in which the equation couldn't be solved analytically, and therefore we considered numerical solutions, or we looked at numerical methods for solving cases that could not be solved analytically. Right? And those were, we of course looked at Euler Euler's method. We looked at the midpoint method. And we looked at Runge-Kutta. Now we're going to get into second order and higher. And those have a general form of, for example, some function of x, a sub 0 of x, times the nth derivative of y, plus another function a sub 1 of x, times the n minus 1 derivative of y, all the way down to a sub n minus 1 of x times the first derivative of y plus a sub n times of x times y is equal to some function of x. So this is a general nth order ODE. And this will be this will be the topic of section 3.3. In sections 3.4 and 3.5, we'll look at how to solve the homogeneous case with constant coefficients. Right? The homogeneous case means that f of x, which was on the right-hand side here, is equal to 0, and the coefficients being constant means that these functions, these a1, a0, a1, do not depend on x. These are coefficients, and they're not dependent on x. So that the homogeneous case was the right-hand side. The function that only depended on x was 0, and a0, a1, a2, etc. are constants. In section 3.6, we'll consider the homogeneous case with non-constant coefficients. I.e., a0 is a function of x, a1 is a function of x, etc. And then finally, section 3.7 and 3.8 will be about the non-homogeneous cases. So that's an overview of what we're going to cover over the next couple of weeks in this class. So this is, I guess, an overview of ODEs, sort of organized in the different forms. And now let's talk about linear dependence versus linear independence. And this comes from section 3.2 of Greenberg's text. And the topic again is linear dependence, abbreviated as capital LD, versus linear independence, abbreviated as capital L, capital I. So just to give you motivation, we need to understand how to recognize linearly independent and linearly dependent sets, because the general solution of an n-order homogeneous ODE with constant coefficients has only n linearly independent solutions. And this comes from Theorem 3.3.3. It's a very important concept, and we'll discuss it in more detail later on. But it states that the general solution of an n-order homogeneous ODE with constant coefficients has n linearly independent solutions. So, for example, if we had the simple case of y triple prime is equal to 0, then we would know that y, just by integration, y prime is equal to some constant a, and y prime is equal to ax plus b, and therefore y is equal to 1/2 ax squared plus bx plus c. And here we have three linearly independent functions of x. Okay, so let's talk about how to recognize linear independence. Well, and I should also mention that the general, well, there are infinite number of solutions, again, for the different values of a, b, and c, but of course there's only 3 linearly independent solutions, and they involve, in this case, x squared, x, and c. So let's look at definition 3.2.1, and this definition says that a set of functions represented by u1, u2, u3, all the way up to un, and they're each a function of x, are linearly dependent if at least one of these functions can be expressed as a linear function of one or more of the other functions. So as an example, we could have the set of functions defined by u1 is equal to, say, x squared plus 1, u2 is 2x, u3 is 4, and u4 is, say, x to the 4th. And you can see that u1 can be expressed as a linear function. Sorry, I meant the second function is 2x squared. So I need that to make it to show an example of a linear dependence. So we can see that u1 is equal to 1/2 of u2 plus 1/4 of u1. So this was u1 here, this was u2, this is u3, and this is u4. So this is an example of a linearly dependent set of functions because the linear combination of u1 and u2, u1 and u3 gives u1. So 1/4 of 4 is 1, and 1/2 of 2x squared is x squared. And so this is the linear combination means that we multiplied a constant or a constant times these two functions to get another function. So now let's look at Theorem 3.2.1. And that says for the set u1 of x, u2 of x, un of x, and the equation alpha 1 times u1 plus alpha 2, alphas are just constants, u2 times x, plus alpha n times un of x is equal to 0. In order for this equation to be satisfied, that this linear combination of these functions equals 0, the set of these functions is linearly dependent if at least one scalar, one of the alphas, is non-zero. In contrast, the set is linearly independent if all the scalars are 0. That is to say, it's linearly independent if the only way to make the left-hand side 0 is to multiply these functions by all zeros. So let's look at an example. So for example, say u1 is equal to x squared, u2 is equal to x minus 1, and u3 is equal to 3x minus 3. And so this is our set of 3 functions. And we have to ask whether alpha 1 times u1, which is x squared, plus alpha 2 times u2, plus alpha 3 times u3, which is 3x minus 3, is equal to 0. And for that to be true, what that requires for each of the 3 values of the coefficients, the 3 alphas. So to answer that question, we need to collect all of the different powers of x. So we have one term that's multiplied by x squared, and that's alpha 1 x squared. We have 2 terms multiplied by x, which is alpha 2 plus 3 alpha 3 times x. And then we have 2 terms proportional to x to the 0 power. That is, that's the constant part, and that's, I should say that's minus alpha 2 plus 3 alpha 3, and that's equal to 0. So for this to be true in general for any value of x, then that means that alpha 1, so there's alpha 1 has to be 0 because all powers of x squared are described here, and for this term to be 0, then alpha 1 has to be 0, and this term has to be 0. The term's proportional to x, as does this term. And so these last two conditions require that alpha 2 is equal to minus 3 alpha 3, and neither alpha 2 or alpha 3 need to be 0. So in this situation, there were not all the values of alpha needed to be 0 in order to satisfy that. So going back to our theorem, the theorem states that the set is linearly dependent if at least one scalar is non-zero, and we found two scalars that could be non-zero, and so this set is linearly dependent. Okay, so back to the definition of linear dependence. Linear dependence is the situation is if for a set of functions, at least one function can be expressed as a linear combination of one or more of the others, and that will be true. We can express this function as a linear combination of this function if we set alpha 2 being equal to minus 3 alpha 3. So let's look at a second example. Let's say that u1 is equal to 3x squared, u2 is equal to x, u3 is equal to x plus 1. So to determine again whether this set is linearly dependent or linearly independent, we have to multiply each by the coefficients and sum. So we have 3x squared times alpha 1 plus alpha 2 times x plus alpha 3 times x plus 1, and that's equal to 0. And so we need to find what is required, what these coefficients are for this to be true. Again, we collect like powers of x, and we get 3 alpha 1 x squared. We get alpha 2 plus alpha 3 times x, and we get alpha 2 plus alpha 3, alpha 3 by itself. Okay, so alpha 3 times 1 is just alpha 3. And for this to be true for any arbitrary value of x, alpha 1 must be 0, alpha 3 must be 0, and if alpha 3 is 0 here, then alpha 2 must be 0. So here's a situation in which all the coefficients have to be 0, and based on our theorem, if all the scalars coefficients are 0, then it's linearly independent. That is, there are no coefficients that, well, each of these functions cannot be, there are no two functions that can be expressed as a linear combination of the other. So this set is linearly independent. And as the last example, let's consider the same set above, U1, U3, and then let's just add one more function, say U4 equals 2. So adding on to our equation here, we would again have 3 alpha 1 x squared plus alpha 2 plus alpha 3 x plus alpha 3 plus we would have an alpha 4 times 2. We would have, so alpha 4 times 2 is equal to 0. And by adding that second constant term, this is now our whole constant. This is the term that's proportional to x to the 0 power. That is, it's constant with respect to x. And this tells us that x3 must equal minus 2, sorry, alpha 3 is equal to minus 2 alpha 4. And neither need be 0 for this to be true. So we found at least one value of the coefficients that are non-zero, and so this set is linearly dependent. Okay, we can this function U4. Well, there are 3 functions, U2, U3, and U4, that can be expressed as a linear combination of each other if U3 is equal to minus 2U4. And for this term, this would mean that alpha 2 is equal to minus alpha 3, and that's equal to 2 alpha 4. Okay, so this is an overview of how to identify linearly dependent and linearly independent functions to determine if a set of functions is either LD or LI.